Hi and welcome to this talk about practical timing side channel attacks. So nowadays, basically everything is hosted somewhere in the cloud. So from renting bare metal machines up to serverless computing, everything can be performed online. Cloud providers are trying to protect their tenants, basically by involving some sort of isolation. But even though the software might be secure, side channels might arise, and therefore we need to discover them and protect against them. So in a remote scenario, an attacker could be co-located within the virtual environment, could run some malicious JavaScript, or could attack an API across the network. Memory compression has a wide usage, for instance, in databases, file systems, but also virtual memory compression is a thing. There exists the compression ratio side channel, and actually yesterday there was a talk about that, which basically exploits co-location between secret and attacker-controlled data, and by observing the compression ratio, an attacker might observe whether a guess was correct or incorrect. In our work, we focus a similar scenario, but we solely use the timing information to observe whether such guesses were correct or incorrect. To achieve this, we are using a fuzzer called compressor, which generates memory layouts and optimizes these timing differences. And with the results of the fuzzer, we use a web API and attack them via remote attacks across the internet. So how does deflate work? So in a basic setup, first data gets into LZ77, which basically removes the redundancy between sequences, and then a Huffman tree is created which removes the redundancy between the symbols. Then you get the compressed data, and when decompressing, it's vice versa. So first Huffman decoding and then LZ77 decoding. So in a simple example, this looks as follows. So LZ77 creates these distance length pairs, and for instance, when starting with a sequence of length 3, you get a pointer or the distance to the first start and the length of the sequence. And the Huffman part now finds some form of optimal encoding for these pairs to further compress the data. So crime actually was tackling web requests. So for instance, the attacker was here trying to guess the content of the cookie, for instance. So there is this known prefix cookie, and the attacker was trying to guess, for instance, with guess. And by observing the packet length, the attacker was able to infer whether the guess was wrong or correct. So what we know so far is that depending on repeated sequences, the compression ratio varies, and this was exploited in various attacks. But how about just timing the compression and decompression in a similar scenario? For instance, by observing the edge cases, incompressible versus low memory. And that's what we did. So we timed the decompression of a single 4 kilobyte page, and you see with a lower entropy, like 4096 times the letter B, we see that there is a significant timing difference. Based on that fact, we created a fuzzer. But before we come to that, I will explain in a high-level overview how such an attack could look like. So you see there is some RAM or some disk page in between, which contains a secret data, and we need some form of interface, some form of API to communicate remotely. So in the first step, an attacker would send some data to a victim application, which will be co-located into the RAM or to some database cell or column, and then the victim's application compresses the content and basically stores it somewhere. And on the next step, to make it exploitable remotely, the attacker needs to have some form of primitive that allows him to fetch the data, so request their own data, which causes a decompression of this data. And the attacker then uses the round trip time to infer whether a guess was correct or incorrect. So how does this fuzzing part now work? So we use a evolutionary fuzzer, which is called compressor, which first generates different memory layouts, or on the first step generating a memory layout with a fixed secret on a fixed position with some known prefix. And the fuzzer basically randomizes the position of the guesses, adds some incompressible data, randomizes the number of repetitions for the guesses, and based on that, these memory layouts will be executed and evaluated multiple times to get some significance of the timing differences between correct and incorrect guesses, and reported back. And based on the result, we found in that first execution, the better memory layouts will be taken as a new population for that evolutionary fuzzer, which generates new samples based off the ones which led to higher timing differences. So what we found by using the fuzzer, by using compressor, was that sequence compression can lead to two edge cases. And the first one is where data is incompressible, the decompression is super fast. And if it's nearly incompressible, but still has to do this Huffman decoding and LZ70 decoding in the decompression step, it is super slow. And this timing delta, for instance, for the zlib library, can lead up to 50 microseconds, which is a high timing difference if you're thinking about remotely attacking that across the internet. So what we can gain of that is that compressor can be used to generate memory layouts to attack byte by byte collocated data within some compressed data from within a database or some in-memory compression. So how would that root cause now look like, for instance, for the zlib library? So you see the correct guess, and there is a current dynamic Huffman block. That's how they call that within the zlib library. And then there is some incompressible data appended. And what happens there is that for a stored block, which is completely incompressible, a simple mem copy operation is performed, which makes it super fast copying data around. So in the case of the other guesses, so the incorrect guesses, for instance, foobar here, a new dynamic Huffman block is created due to the repetition of our guesses, and the incompressible data is within the same dynamic Huffman block, leading to the case that it has to traverse the full Huffman tree and then traverse the sequence compression for incompressible data, and leads to a super high timing difference between those two cases. In our paper, we were observing different case studies. So the first one was on memcached, where we hosted a PHP application which leverages memcached to cache some in-memory data, and there we placed some secret string in memory and collocated data from a remote API call. So there was a store call, and the collocation happened in the chunks from the slab allocator of memcached. And we were exploiting that whole thing 14 hops across the internet. So we were sending network requests there and observing whether the guesses were correct or not. A similar scenario was performed in PostgreSQL. So a web API allowing it to send requests there, store data in memory, in the database in that case. And again, data will be decompressed. And on the decompression, we again have super high timing differences. And our last case study was exploiting virtual memory compression with ZRAM. And there we had to find a way to swap out pages from JavaScript and collocate these 64-bit heap internal pointers of Google Chrome next to a Decca-controlled data. So this requires a bit of JavaScript fiddling until you can collocate the data. And with that, we were able to recover the 64-bit heap internal pointer, basically break ASLR with that. So on a simple perspective, so how would that look like, for instance, for the memcached case? So you see we have a single guess, so we have this known prefix cookie, and you see for the first guesses, this is in a similar range. And once it comes to the correct guess, we have a significant speed up from the response time and can super easily differentiate those two cases and recover the secret. So as you might imagine, if we have like 50 microseconds of timing difference, we only require about 100 requests per guess to recover that secret, which makes it more practical than previous attacks in that range. So how would we mitigate such an attack? The first thing would be to not compress secret data with attacker-controlled data. And that could occur, for instance, there are papers which, for instance, do some taint tracking to observe whether we have such a collocation, but that could be also avoided if, for instance, the defender is trying to mask some data. There's also some work discussing if we remove sequence compression, so solely having the Huffman encoding part to avoid such attacks. One could also, and we found that quite effectively, place the same secret multiple times in memory at random location, which makes it harder for the attacker to fuzz it with compressor, or also add some random amount of data, some type of padding. Of course, if you're attacking from the network side, you can do some rate limiting or some, I don't know, deep packet inspection to discover such attacks. So concluding that talk, we have seen that edge cases in compression algorithms can lead to significant timing differences and can be exploited. In our paper, you will see we evaluated that on a large scale on compression algorithms that are based on SZ77 and Huffman encoding. We also show how the bitewise leakage is possible in such scenarios, how compressor can optimize these timing differentials. You will see in the paper a remote covered channel over 14 hops, and then also more details on the attacks I just mentioned. And if you're interested in the source code, go to GitHub. Everything is already pushed there. Thanks for your attention, and I'm ready for your questions.
Thank you very much. Let me ask the first question. Another defense would simply be you use an algorithm that has the same length, path length timing on all paths, right? So algorithms designed for this. How much would that actually affect regular operation if you just put in a leak-free algorithm?
A leak-free algorithm, yes. So yeah, there's an implementation of safe deflate which does a similar thing, but I think the timing overhead is about factor 600. So you need to decide whether you want to have that or not.
Okay, thank you.
Great. Hey, thank you. Wonderful work. So I was interested by your point about the trade-off between sequence encoding and then page compression, because at least in a lot of data analytics, the sequence encoding is much, much better because you can still do queries on this data. You know, oh, look, I have a run length encoding. Gosh, I can skip over all those things. Mm-hmm. So I'm wondering about your thoughts about sort of this work in the context of like column stores and data analytics and all those trade-offs of formats.
Yeah, so we contacted, for instance, the PostgreSQL people. So they thought that there might be some scenarios, so within the same cell, for instance, in structured data, where you could have such a case that you can collocate data. And for instance, in Postgres, it's solely based on sequence compression, their algorithm. So I think they will keep that because there are also extensions providing columnar storages and columnar compression. I think also the one library from Facebook does similar things. RocksDB. So the feedback was they don't think it's that dangerous, but yeah, I guess you gain more from the compression and like the part with the querying that Michael mentioned. So I guess it will it will be still there.
Great, thank you.
Yeah. Mm-hmm.
Thank you. Two questions. First, why do you need fuzzing to do this? Can't you just have some kind of enumerator of input, or is it the space of input is too big to actually generate those attacks? And second question, can you explain a little bit more the memory layout constraints that you're talking about? Because I didn't quite understand.
Mm-hmm. So yeah, of course we started off by doing that manually, but we found that there are too many variables to do that on a manual page, because we were like mutating the number of guesses, mutating the position within the memory. We were also mutating how much memory we append to trigger such edge cases to see how much memory is required to have such a stored block. I think that was a random search, so I guess we were faster doing it with the fuzzer. To your second question, yeah, so these are the parameters we are using for the fuzzer. So we are starting off with some nearly uniformly distributed memory, and then we are placing on the first data like the secret string, and then start with the placement of the guesses and the number of repetitions, and we also play around with the memory layout inside there. So we do also some tweaking there. And based on that, we run the fuzzer as described before.
Is it because the layout, the compression itself depends on what layout it is?
Yes, yes. So as you have seen before from the previous slide, so you always need to append that stored block. But yeah, we can take that discussion offline as well.
Thank you very much. Thanks. Let's thank the speaker again. Thank you, Martin.